Now let's go to chapter 2, and chapter 2 now will consider motions in one dimension. Okay, this is a very simple motion, so the motion can only happen along a straight line, so you can either move forward or move backward. So how do you describe physics in this situation? First of all, we are already going to consider kinematics. Okay, so we do not consider the agent which causes the motion, like force, which accelerate particles or things like that. We only concentrate on the kinematics. So we will use the particle model. It means that we'll treat the particle as a point-like object, okay, as mass, but its point, its size is infinitesimal. So this is, for example, pictorial representation of motion of a car. It's moving forward and then moving backward. This is a graphical representation. So here you take some position as a reference point, and then the car is moving. The x-axis is the position of the car, and the y-axis is time. So it's moving, and then from here you're going backward, and the motion as a whole generates such a smooth curve. This we can compare these two. One is the graphical representation. The other is this is pictorial, and this is graphical. So here you need some reference point. Okay, so you take this as a position from which you begin to measure the distance or the position of this car, and it's moving forward and moving backward, and here it's moving forward and it's moving backward. Or you can just give some tables for the position of the car at various times. At position A, it was, for example, at the origin. Not origin, but at time 0, initial time, the position was 30 meters, and it was moving, and then just the position begins to decrease like this. So all three gives you the same way of describing the motion of the car. So, but all these three is not enough to give you a accurate description of a car, and you can use some mathematical representation to describe the motion of a car. And the first fundamental basic quantity is the position as a function of time. So it tells you at time, arbitrary time t, where was the position of x. Okay, so for example, if you have x ta, it means that at time ta the position was xa. Okay, xb tb means the position of the car at xb. Now from this position you can define a very important quantity called displacement. Okay, that is the difference between the initial position and final position. So delta x, which is called displacement, is defined as final position minus the initial position. So assume a player moves from one end of the court to the other bag, and distance here, distance is different from displacement. Distance is twice the length of the court. Okay, distance is just absolute distance that a particle or this man, for example, has moved. But displacement is 0. So okay, so you start from xi and you came back x final, and x final position and x initial position are the same. So the displacement is 0, but the distance is twice of this distance. Okay, so if your distance is d, then the distance d, let's call it d, is equal to 2d, but the displacement is 0. So here is just the exhibition of this it is this concept using this basket prayers. Okay, so assume a prayer moves from one end of the court to the other back, and distance is twice the length of the court, and displacement is 0. So comes these quantity vectors and scalars, and vectors are quantities that needs both magnitude and direction. Okay, so the vector, in order to specify a vector, you need not only the magnitude but also its direction. In one dimension, for example, you can use plus or minus to indicate vector direction. So the plus means that the direction is positive, minus is direction is negative. But the scalar quantities are completely described by magnitude. For example, so the distance that was mentioned is scalar quantity, and the displacement is vector quantity. Now, given a distance or displacement, you can define a very important quantity called velocity. Okay, so it means how fast is the particle moving. Okay, and average speed is a scalar quantity, because this one is scalar quantity, is d divided by delta t. Okay, so speed is not a vector, it has no direction, but average velocity is a vector quantity. So it means that average velocity, this is velocity now, not a speed, is going to be defined by delta t over delta x. Okay, so that is the definition of average velocity. So it's basically saying how much per unit time is the displacement changing. So let's elaborate on this using this car moving. So the motion of particle can be specified if its position is known at all times. So consider car moving back and forth around x-axis. The figure is pictorial. We first use the pictorial representation. So it moves its initial position here and move back now. Or in graphical representation, here, for example, it's x versus t. So here, for example, when car is moving forward, okay, the time is delta t and delta x is this. So v average velocity is equal to delta t over delta x. But where it's familiar, if you think of this x and y, and this right is the slope of these 2 points. Okay, so the average velocity is the slope of these 2 points here in the graphical representation. Or you can have the tabular representation. So all these three you can calculate, for example, the average velocity. So here, now we are going to formally define average velocity, which is defined in this way. Okay. So here x indicates just a line. So in one-dimensional motions, we'll just you can just derive this. So that's v means this motion along x-axis. When you consider a plane, then you need velocity along x-axis and y-axis, and then later we'll use the notation vx is velocity along x-axis, vy or velocity along y-axis. But for one-dimensional motion, there's only x axis, so you can skip this x without too much confusion. So here you see delta x, which is xf minus xi, can be positive or negative. It means average velocity can be positive or negative. We call that v is the vector particle, so it can be either plus or minus. It can be moving along plus axis, moving forward or moving backward. So the meaning of the average velocity can be seen best in this graphical representation. As I mentioned, the delta x over delta t, which is the average velocity of these 2 points, is the slope of this line connecting the points. So now what is the displacement? So displacement is given by v average. So delta x is v average times delta t. So delta t, if I think of very small section of this, for example delta t, very small, then it means that delta x is this multiplication of v average times t, so it is the area of this. So if I add all these up, it should give you the displacement. So displacement of a particle during time interval ti and tf is the area under the curve of these initial and final points. Okay, so what's wrong? Okay, anyhow, let's move on. So find the displacement. Here is the example: average velocity and average speed of a car between position A and F. Where is F? Here. Okay. So the displacement of the car initial was 53. I'm 30, and final position is minus 50. So the displacement is minus 83. The average velocity is Tf minus Ta times Tf minus Ta, so minus 1.0. So on the average, it means that on the average, the motion is along the negative speed. The car's average speed, however, is 50 times all the distance that has moved. So it has moved from here to here, the distance plus now, because we are now calculating distance and this distance here. So it should give you 127, and average speed is 2.5 meters per second. A Jaguar runs in a straight line. Let's try a second example with an average velocity of 5 meters for 4 minutes, and then with average velocity of 4 meters per 3 minutes. Okay, so what is the magnitude of final displacement from the initial position? So use this relation here, and delta x is 1. So first, the speed was 5 meters per second, and it has moved 4 minutes. So, but recall we are using always SI units, so you should convert this into sec. So the result is this one, and the second motion was moving at a 4 meters per second times 3 meters, so it should give you, so the displacement should sum up this one, so it should give you significant figure 3. So this one is 1200, and this is 7.20, I mean 720, so it should give you 1.992, only we have meter. times, I'm sorry, times 10 to the 3 meter. What is the magnitude of her average velocity during this entire time? So it has moved 1.92 times 10 to the 3, and the total was 4 plus 4 minutes and 7. And you also you have to convert this into sec, and the answer is this one. Now we have defined average velocity, but the average velocity cannot give you the total accurate description of the motion. So you need a instantaneous velocity, and let's see how instantaneous velocity can be defined. Instantaneous velocity means literally it means that the velocity at that moment. It's not average interval of time, but at that moment. Okay, so here is the, for example, geometrical meaning of instantaneous velocity. For example, suppose I have xa and xb, and suppose b is approaching point A. Now, when b was at here, the average velocity of slope of this, okay, when b moved forward, backward here, and then at point B here, the average velocity slope of this, and now I can continue this process, and if this B point almost approaches at A, then what is the slope? Then slope is this is the slope of this tangent line. Okay, so instantaneous velocity at A now is defined as a slope of this this curve. I mean slope of the tangent of this curve. Okay, so instantaneous velocity is the limit. For example, here from here as it approaches here, the average velocity was delta t over delta x, and mathematically you can say velocity at ta is the limit when this point approaches at point A. So it's the limit when delta t goes to 0, or delta t over delta x at point x is equal to xa. Okay, so that is the mathematical definition of instantaneous velocity, and the geometrical meaning is that the instantaneous velocity at ta is slope of this tangent line. So here is what I have just explained, and in mathematics this one is nothing but the differentiation of x with respect to t. Okay, so here are some examples, I mean intuitive examples of instantaneous velocity. Here the slope is positive, so Vx is positive, and here for example the slope is 0. It means that the velocity is 0 here. Here the slope is negative. It means that it begins to move backward. Here it is positive, begins to move forward. Here it stops and then begin to move backward. Okay? So that is the intuitive example of instantaneous velocity. Of course, you can also define instantaneous speed, which is a scalar quantity, and that is the magnitude of the instantaneous velocity vector here. So instantaneous speed, for example, if you write the instantaneous speed as a Vs, then is the magnitude of the instantaneous vector. Okay, So it is always positive. Speed can never be negative, but v itself can be positive or negative depending on whether it is moving forward or is moving backward. So this is an example. Okay, the position of particle moving along the x-axis varies in time according to the expression x is equal to 3. Find the velocity in terms of at any time t. So you have x is 3t squared, and velocity at any time should equal to the differentiation. I told you it is differentiation, and if you differentiate t squared, you have 60. Okay, so differentiation. This is the expression for the instantaneous velocity. So at any time, you can specify what is this velocity. So here Vx is 6t, and on the other hand, if you calculate x average here, you have to calculate delta t and delta x. Delta x is here it is, delta x is calculated here. X final after time delta t is this one, and if you differentiate, well, this is very simple. This is t squared plus 2t delta t plus delta t squared. So if you subtract x initial, which is 3t squared, that gives you this expression. So that is delta x. So that is delta x times delta t, and that is the expression for the average velocity, whereas this one is the velocity is the instantaneous velocity at any time. So this one is just simple examples. So let me just skip it. And now comes important another important definition. And following the same procedure as the velocity, now you can consider a variation of velocity during time interval delta t, and that is called acceleration. So acceleration, so that is average acceleration, is delta x over delta t. So this is precisely following the same definition as v average is equal to delta x over delta t. Of course, you can also define the instantaneous. At any time t, it is limit delta t goes to 0, delta t over delta vx, the x direction. So it is dt over dvx. So the same procedure as the defining average velocity and the instantaneous velocity. Okay, so that is the definition of instantaneous velocity. And now, if I use this vx was already a differentiation, so ax is differentiating the position twice with respect to time. So in mathematics, it's called second derivative. If you don't know this differentiation, you must learn. Okay, there's nothing that I can do about that. So here, again, as in the case of the position versus time, if you draw a plot of velocity versus t, then the instantaneous acceleration, for example, at this point is slope of this line, tangential line, and the slope of this line and slope of this line. Here the acceleration is positive, here acceleration is 0, here the acceleration is negative. Okay, so you can repeat this at every point here, okay, and then draw a diagram of t versus ax. Okay, so here, for example, here the slope is 0, so it starts from 0. Okay, so at this point here, the slope is highest. If you see from here, the slope starts from 0, and it begins to increase, and then here it also begins to decrease, and it becomes 0 here. So here the acceleration is 0, so that it should be here, and the acceleration begin to increase, recall this is slope, so this increase and then decrease and 0, and then becomes negative and 0 here. Here also is flat, almost flat, so it should be 0 here. So that is a plot of ax versus t, which corresponds to velocity versus time graph here. So for the negative acceleration does not necessarily mean that the object is slowing down, because if the velocity is negative and the acceleration is negative, then the object is speeding up. So if the velocity and the acceleration are in the same direction, means v could be plus, acceleration plus, and this one is accelerating, and they can be both negative. This is also accelerating. But for example, if the velocity is positive, so velocity is positive and acceleration is negative, it means that velocity begins to decrease. Okay, so it means the acceleration slows down. The negative acceleration slows down. So the opposite case is also true. The particle is moving minus direction, but acceleration is positive, then it also slows down like this, and then maybe turn back here. Here, originally it's moving forward, but acceleration is negative, so it has to slow down and maybe turn like this. Okay. So here is an example over here, and then you have instantaneous acceleration to be dt over dvx, and if this one is gives 0, so it gives minus 10t. So that is the expression for the acceleration at any time. So I'll hand out this lecture notes so you can just see, try to do these examples by yourself. It's not difficult, it's just the application of this definition of this velocity and acceleration. Now here comes the most important part of this chapter, and that is for a constant acceleration, you have this expression, this four expression, you have to memorize it, almost memorize it, for example, to prepare for the exam. Okay, so this one is velocity versus time, this one is position versus time, this one position and velocity, and this is position and acceleration, and this is velocity versus xf. So this is very important relation, so I'm going to derive these things very quickly. So let's start with 2.10. Okay, so that is the start from the definition. So we have a, let's skip, for example, the index x here because the dimension is only 1, so this is x direction. So a average we define to be delta v over delta t, and delta v is vf minus v initial over delta t. I'm going to take it to be t, so t initial is always 0 and t final is t. Okay, but the important thing is this here for a constant acceleration, this all corresponds to constant acceleration. For constant acceleration, average, since the acceleration is constant, average should equal to a. Okay, because it is constant. So here from this equation, you immediately first get vf is equal to vi plus at. Okay, so this multiply this, put this in here. Now let's derive 2.12. Again, start with average is equal to delta t, which is t over xf minus xi. So it gives you xf is equal to xi plus v average t, delta t. I take always the initial position to be 0, final to be 0. Now, since the acceleration is constant, velocity is increasing steadily. It means that the average velocity should equal to, since this is moving very steadily with constant acceleration, it should be half of vi plus vf t. Okay, so that is the second expression. So here it is essential to recognize that for a constant acceleration, the average velocity is equal to, because it is increasing steadily, it is half of initial plus final. Okay. Now 213 comes from, if I put this, you have this expression here. Okay, so I'm going to use this, substitute this expression into here and see what happens. So xf is equal to xi plus here 1/2 vit plus here 1/2 vft, and vft is what? Xi plus 1/2 vit plus vf is 1/2 here, from here vi plus at, and that gives you xi plus here you have 1/2 I'm sorry, we have t, so 1/2 t, 1/2 t, so it gives you vit plus here 1/2 at squared. Okay, so that is the third expression. Now for 214, the best way of calculating this thing is first use 2.10, from which if you just push these things to the left hand side, we have v final minus v initial is equal to at. Okay, and from here 2.2 you have what? Vf plus vi is equal to what? Here you have 2 xf minus xi times 2 over t, so it's 1 over 2 over t times xf minus xi. Okay, so if I multiply these two equations and use this very basic formula, a plus b, a minus b is equal to a squared minus b squared, then you have here vf squared minus vi squared is equal to t cancels. Okay, so it gives you 2a xf minus xi. So if I put this into right hand side, you have vf squared is equal to vi squared plus 2a xf minus xi. Okay, so that is this expression. So please go through this procedure and just you have just remember this formula. Also there is some this is an example, and using just definition of the basic quantities. A jet lands on an aircraft carrier at a speed of 140 meter per second. Whenever it comes here, you always convert it to mile. If you have to standard unit meter per second. What is its acceleration if it stops at 2 seconds due to an arresting cable that snags the jet and brings it to a halt, and ax is t of vx minus vt. The acceleration is constant, so its average is 0 minus 2. So the acceleration, it has to decelerate at this rate to stop. And this is also example using this one here expression. the final position is initial position times the final velocity times initial velocity. So initial is this one, final is 0, so xf is okay. So this one is application of this here. So this is also very useful to remember this formula. So this in this example, a car traveling at constant speed passes a trooper on a motorcycle hidden behind the billboard. 1 second after the speeding car passes the billboard, the trooper set out the billboard to catch. So you just use these two relations. Okay, so this car xc is equal to xc final is x car initial plus v car initial t plus 1/2 acceleration car over t squared. For the trooper, you have x trooper is equal to x trooper initial plus v trooper initial t plus 1/2 a trooper t squared. Okay, and you have just put the correct numbers for these. So for example, suppose the car, suppose I take this position to be 0. Okay, this one is x is equal to 0 position. Then the car starts from here at t equals 0 to here at a constant speed. So it starts at initial position 0 at a constant speed. Okay, with no car. But here the trooper starts from initial position, which is minus 1 sec. So it tried to catch up this car 1 second distance. So this should be the car speed is 45. So this should be minus 45. Okay, so this is x equals 0. So it should be minus x5. It accelerates. The initial velocity is 0. And it accelerates at 3 meters per second. So you have this to catch this one. The position of the trooper should equal to car. So you have minus 45 plus 1/2 a, which is 3.00 times t squared. That should equal to VCIT. So it's 45 meter times t. Okay. So that is a second order equation. And you can try. So that should be minus 45, and this one is 0, and this one is 0. So you have this equation, and you have the formula for the root, okay, and take the positive sign. So after 31 seconds, it will catch up with this. Now, in one-dimensional motion, one important motion is freely falling object. It means that the body falls freely under the gravitational influence. So A is equal to minus g, because usually this one is taken as positive direction. Because always the Earth always attracts the particles, so you should use minus g. Okay, and it is known that Galileo performed many systematic experiments on objects moving on inclined planets. So with careful measurement, he showed displacement of objects starting from rest is proportional to the square of time interval. So that is the famous relation x is equal to g constant times t squared. Okay, we have treated this example in chapter 1. So a freely falling object is object moving freely under the influence of gravity. Okay, and that is downward, accelerate downward means if I take this as a positive direction, it should be a should be minus 9.80 meter per sec squared. And a freely object, there are, can be many cases of freely falling falling object, it can be dropped. Okay, you just can drop it. You can just throw it, and then it falls down, and you can just throw it throw downward from the beginning. So this is an example. Stones from up top of building is given an initial velocity. So you have v initial velocity is 20.0. So it's plus. So it means you throw it upward. The stone is launched 50 meter above ground. It means that if I take this as x equal to 0, then let's call it y here, because this is a vertical direction. So y initial is equal to 0, okay, and the stone just missed the edge of the roof on its own, okay, and then it falls down. So from these two initial conditions, since this is a constant acceleration motion, you have y final is equal to y initial plus vit minus 1/2 gt squared. Okay, so that you can use this formula to solve anything. Oh, and of course, v y direction final is equal to v y initial minus a gt. Okay, here g is of course 9.80 meter per sec squared. So for example, I'll not go through all the examples, but just for example, when you start from here, when does it reach the maximum height? Then the maximum height of the maximum height will be reached when the condition for this begins to fall down. So the velocity changes from positive direction to negative direction. So the condition for that is Vy is equal to 0. Final is equal to 0. Okay. So using this formula, put this condition, and after 2.04 sec, the ball will reach its maximum height. Okay. So these are all the same example, and again, let me just skip this.
Okay, so as I already notified in the guide for first lecture, these topics, vectors and coordinate system, let me use is in chapter 1. But as I said, it's better to discuss this after the one-dimensional motion. Okay, so we discussed one-dimensional motion, and suppose a particle is moving in this plane. Okay, so particle is moving in this plane. So how do you describe this particle? So of course, first you have to describe this motion. You have to know where at each time this position is. Okay, so to specify the position, you need first a coordinate system. Okay, so this coordinate system. Okay, so you can usually take a Cartesian coordinate system where this is perpendicular and this origin can be anywhere. Okay, then at specific time t, then the position is here, and that position physically is described by these so-called vector at r time t. Okay, so this is called vector. Okay, so in this part of the lecture, I will describe what is vectors and what and the coordinate system. Okay, so here is the contents of this portion of the lecture. So I'll first describe coordinate system, and then This one is called vectors, and in physics, physical quantities can be classified into two categories. One is scalars, which I'm sure you have or heard about. This one is the physical quantity that only has magnitude, okay? And vectors. And this one has magnitude plus some direction, okay? So for example, here, at time t, it may be here, but at time t0, for example, the vector original position was at here, then you describe it as rt0. Okay, so it has magnitude, which is the length of this, and then the direction. Okay, and then I will describe some properties of vectors. Okay, so just like numbers, you add numbers like 1 plus 2 is equal to 5. If you have two vectors, you can add two vectors, and that gives you another vector. And I'll explain in detail how do you add two vectors. We know very well how to add two numbers, but this notion can be extended to the vector addition, vector subtraction, vector multiplication. And there's all mathematician has invented all these things. For example, you can have 1 times 2 is 2, and you can also product these two. So one is called dot product, which will appear in the when we discuss concept of work, and the other product is called cross product, which will appear when we discuss the angular momentum and torque. Okay, and then finally I'll give lectures on components of vectors and unit vectors. Okay, so these are all mathematical materials, but in physics, physics use the language of mathematics, and you need to know very well about these concepts. Okay. So the coordinate system is used to describe the, and in order to describe this motion, you need now a more refined definition of coordinate system. And coordinate system can be used to describe the position of a point in space-time. So suppose a particle is here, and I want to specify this position, then you introduce a coordinate x and y. Okay, and then you call this as x coordinate and this distance as y coordinate. And so you first have to introduce a coordinate system. And in coordinates, to describe the coordinate system, you have to first specify a point. This is called a reference point. Okay, you can either take this point to be your coordinate point, or for example, I can take this point. So it is up to you. Okay, at any point you can take the reference point. At any point you can take it as a reference point, and then you can from in this coordinate, the x coordinate will be here and the x coordinate will be this much. And here you have 3 points, and a reference point is chosen here. So here is P and xy, arbitrary point xy. Here is minus 3.4. So it's 1, 2, 3, and 1, 2, 3, 4. So given a position here, you can represent it in two different ways.
I can either you can use x and y, which is called Cartesian coordinate, or you can use r and theta. Theta is the axis angle of this with respect to x-axis, and r is the distance. So using the Pythagoras rule, you can see that r square is x square plus y square, and x tangent theta is equal to y. Okay, and the relation between, so theta is tangent inverse x over y. So the relation between x and y and r and theta is the following. Okay, so you can either work in the Cartesian coordinate, or this coordinate is called a polar coordinate. So that is the relation between r and theta. X is equal to r cosine theta, y is equal to r sine theta. Okay, so tangent theta is equal to x over y. So r is square root x square plus y square, and tangent theta is y over x. So here is the example. So the position is here. You have chosen your reference point to be here, and either you can represent r, which is distance, and theta, or x and y. Okay. So here again, let me mention about scalar quantity. Is just a quantity that only has a magnitude. It doesn't have any direction. A vector quantity is described by a magnitude and its direction. So, for example, this gives you the good example. How is vector different from the scalar? Okay, so a particle moves from A point to B along the path shown by the dotted. So it's moving a very completely twisted line like this, and the distance is traveled by this one. So the total length of this twisted curve gives you a distance, but the displacement is just xb minus xa, which is vector. So I usually vector. So the vector is this one. So the magnitude of vector is distance of this. That is the magnitude of vector. And then the distance direction is in this direction. Okay. So for vector notation, usually you put an arrow on top of it, okay, or just boldface. And for magnitude, you just put two bars in front and in the back. Okay. So these are so let's summarize for some properties of vectors. So suppose these four vectors are given. Now I can always parallel transport this into here, and they match. Okay, so two vectors are equal if they have the same direction and magnitude, and you can always parallel transport a vector. So in this case, if I just parallel transport this, it will just match this one. So all four vectors are treated as equal. Now, if two vectors are equal, if they point along the same direction, and if the magnitude are the same. Now, you also need how to add vectors. Okay. So when adding vectors, their directions must be taken into account. It's not a sum of numbers. You also have to take into account their directions. So their units must be the same, and there are graphical method or algebraic method. For a graphically add two vectors, you need, for example, suppose you have A, which is in this direction and this magnitude, and you have another vector b, which for example is in this direction. So how do you add these two? Okay, the addition is very simple. You just parallel transport. Record the parallel transport does not change. You parallel transport this and match this starting point with the second one like this. So you parallel transport this and like this and just connect these two. So that is the vector sum of A plus B. Okay, you can see more clear here. When adding two vectors, you start with A and you just, wherever the vector B was, you just parallel transport it and just match this arrow with the starting point, and R is the resultant vector is given in this way. You can apply this to many vectors. So this one shows you how you can add these four vectors A, B, C, D, and the final vector is given by A plus B plus C plus D. Or you can add this one. Actually, this addition of A and B and obtaining this one is actually, if I push this one and put it here, parallel transport it, and then this one is just the diagonal of these two rectangles. Okay, and that shows that A plus B, the addition of vectors satisfies some rules, and A plus B is equal to B plus A. That is called commutative. You can exchange the direction. So either you can consider A plus B to be R over B plus A, and the results are the same. And if you add this one, you have three vectors and add B plus C first and then add A, that is also equal to add A plus B and then add C. Or you can add the same as A plus C first and then plus B. Okay, and this one, they all give you the same vectors here, and that is called associative property. Okay, so here this is a graphical representation. Here you first add B plus C, okay, B plus C, which is this one, then add, or you can add A plus B first and then C, and this vector and this vector, sorry, are the same. That is called associative group. Of course, when you add two vectors A and B, they must have the same units, so they must represent the same physical quantities. For example, you cannot add a displacement to a velocity. And also you can define a negative vector. The negative vector is defined as the vector has the same magnitude is the same, but direction is opposite. So if you vector A here, you can always consider a vector has the same magnitude but pointing direction. So if you add these two, then you have just came back to the same point and it gives you 0. 0 here is not just number, it's 0 vector. So more precisely, it should be called 0 vector. And then you can consider subtraction of the two vectors A as the sum of A plus minus B. Okay, so this one is A, and if you want to add B, you add, if you subtract minus B, you add minus B. If you want to subtract B from A, you add A to minus B, and that is the subtraction of C vector here. So C here is A minus B. You also can consider a multiplication by a scalar. So if you have a vector A and multiply by C, that has the same direction as A, but the magnitude has multiplied by C. Okay, so C. So CA has the same direction, but the magnitude has changed by a factor of C, where C is just some constant. Now, graphical addition was very intuitive, but it's not recommended, and more accurate method is this component method. So this is more mathematical, and that will be used in this course. And you can define a component of a vector. So given a vector and reference coordinate system, you can define component of x component and y component a this. Okay, so x component is projection of this a vector into x direction, and y component is projection of this into y direction. So ax and ay are component vectors of a. Okay, and the magnitude of this ax is the magnitude of this x vector, and y is the magnitude of this vector, is the components of a. So a, if you see an expression like this, ax and ay, it means that the a has x component of ax and y component of ay. Okay. So a here is ax plus ay. So you can either represent ax plus ay, but more conveniently you can just write it, just introduce a bracket here and call it ax and ay. So it means this one is component of ax and this is component of ay. So here, from here you see that ax, if the magnitude is called a, then ax is just a cosine theta, and ay is a sine theta. Okay, so a vector now can be represented in component form as a cosine theta, a sine theta. Okay, so that's what is written here. Or this is ax and this is ay. So a, the magnitude of a, according to Pythagorean rule, should be like this. The angle that it makes with respect to x-axis is this ax over ay. So the component can be either positive or negative. So here ax and ay are positive. Here ax is negative, ay negative, ax positive, ay negative, ay negative. Now it's very convenient to introduce a unit vector. So you have, if you have coordinate system, a unit vector I. So unit vector I is the magnitude 1 and direction is along x direction. And another unit vector J has magnitude 1 and direction along y direction. Okay, so I and J are two unit vectors along x and y directions. Okay, in 3 dimensions you have I, J, and K. K is the unit vector along z axis. So now you have many ways of representing A. So A was, let's just summarize it. First written as AX plus AY. Now AX, magnitude is AX, and direction is I. So this one is, you can write it AX as AXI, Y as AY J. Okay, and in component form you can just write it AX and AY. So these are all equivalent representation of a given vector A. You can sum these two vectors A and B in component form. So A has AX, AYJ, B has BX, BYJ, and the sum of these two has component AX and AY. So graphically you can see clearly here AX is AX AY, BX as BX, this is BX, and BY, and R has RX, which is sum of these two, and RY, sum of these two. And of course, the magnitude of the vector R is this, and that should be given in this way, and tangent zeta is given this way. In 3 dimensions, you can have I, J, K, and R, and zeta. So these are just trivial examples. You have given A and B, and A and B, okay, and tangent zeta here. So these are all just trivial examples. So I'll just skip these things, okay, and this lecture note will be distributed, so you can just I think you can just look at it and study by yourself. Okay, so let's stop here for the first lecture.